Good evening, everyone. Welcome to the second live interactive session. Since it's just 5:56, we'll wait for 5 more minutes so that we can let others join. We can allow others to join, and we'll start at sharp at 6 p.m. It's sharp 6 p.m. and I'll welcome you again to the live interaction session number two for the course Nanotechnology in Agriculture NOC 25 BT1. My name is Amit Ukle. I am Prime Minister's Research Fellow in the Department of Mechanical Engineering, IIT Tirupati. The course instructor for this course is Professor Mainak Das, professor in the Department of Biological Sciences and Bioengineering, BSBE, IIT Kanpur. So, just before we begin, these are the few things which we do every time. This session is basically to boost your performance. This is not compulsory, but we highly encourage you to do it. We request you to be respectful in the chat. Any questions you have can be asked at the end of the session. Videos will be uploaded on YouTube. You might have seen the videos of first lecture already. So, like many of you had a doubt last time, so I rechecked what is the criteria to get a certificate. So basically, you have 8 assignments, each for one assignment for each week. Out of the 8 assignment that you submit, best of six will be taken, and that will form 25% of your total score. Then the remaining 75% will be on the based on the exam that you will be giving. So you will have to be paying 1,000 rupees or something for that exam. Based on the exam, for that exam, you'll have to go to a center, and on that basis, you will get 75% of your marks. And to be eligible for the certificate, you need like 10 out of 25 in your assignment score and 30 out of 75 in your final exam score, and the total score should be more than 40. So all the three criteria should be met, and only then you will get the final your final certificate. So uh, since I think so, if you have any doubt, you can unmute yourself and ask right now. So if you have any doubt regarding the passing criteria, else we'll move forward. um, I'll just check if anyone has put in the chat. um, yeah, nobody has put in the chat, so we'll move to the this week's um, this week's agenda. So today we'll discuss the practice assignment 2, and then we'll move to question and answer. This is a very short and sweet week. So if you have any questions regarding nanotechnology or anything, we can take them up as well as in when the question comes. This is the course outline. This is a 8-week course. We are in the second week. This week is mainly related to overview of nanotechnology. This is one of the very simple uh, parts of the course. So we'll be moving with it. So these are the week 2 assignments. So the first question is, in dash all the three dimensions of the nanomaterials are in the nanoscale range. Nanoparticles will dash nanoparticles will come into this uh, classification. So whether it is zero dimensional nanomaterials, one dimensional nanomaterial, two dimensional nanomaterial, three dimensional nanomaterial. So, any guesses? Okay, so so I'll just give you a hint. So there are four types of nanomaterials. Nanomaterials are classified into four types. So basically, there are zero dimension nanomaterials where none of the dimensions, so all x, y, z, are uh, in the nanometer range. Then we come into the 1D nanomaterial. These are the one dimensional nanomaterial. These can be like nanowires mainly. So here one dimension. So so either x, y, or z. Out of the x, y, and z, at least one dimension will be more in the more than nanometer scale. So it will be in the micrometer scale per se. So these are like one of the dimensions more than nanometer. All other two are there in the nanoscale. So then we go into the third. These are the 2D nanomaterials, which are nanosheets. So you can see here x and y are more than nanoscale. Only the z dimension is uh, in the nanoscale. So that is why it is called as the sheet. Then there is the third type of the fourth type of nanomaterial, that is the 3D nanomaterials. In this, basically all the dimensions are more than the nanoscale, but still they are called as a nanomaterial. So basically, why is that so? So basically, what happens is the feature size. So even though the size of the entire nanomaterial is more than nanoscale, but the feature size, the minimal the feature size which actually give the uh, uh, which actually are the building blocks of the nanomaterial are in the nanoscale. So it will be like some interconnected structures. So in this, but the interconnection, the bonding, there will be some wires or something like that, that will be forming the basic building block of this nanomaterial. In that case, it is called as a 3D nanomaterial. So in this case, the question says that there is all the three dimensions are in the nanoscale range. So the answer is okay. Any guesses? So the answer is A, zero dimension nanomaterial. Here, all the dimensions are less than are in the nanoscale range, and it is called as zero dimension nanomaterial. Again, as I said, again repeating, this is a very important question. This type of questions are asked many times. So more than one. So one axis is one dimension nanomaterial. If two axes are more than nanoscale, two dimension, and if all the three axes are more than nanoscale, it becomes a 3D nanomaterial or a bulk nanomaterial. But the building block or the building or the feature size is in the nanoscale, so that is why it is called as a nanomaterial. These are the very important questions. This will be asked. This get asked in many places. So this is the first question. Moving to the second question, ZNS, ZNO, CDS, CDAC, and CDT are related to dash group of semiconductor material. Group 2, Group 4, Group 2, 4, Group 2, Group 6, Group 2, 6, and Group 7. So, any guesses? Okay, so this is how the nanomaterial is grouped. So basically, when you have if you have a binary structure, so if you have a 2 6 structure, you have two, that is called as a binary semiconductor nanomaterials. If you have three groups, so like you have group 1, group 3, and group 6, CuInSe2, so these becomes a ternary semiconductor. So these are examples. And then you can also have a quaternary semiconductors that will have group 1, group 2, group 4, and group 6. So in this, since it's a binary structure, it will be a 2 4 sorry, it will be a 2 6 semiconductor. So the answer is C, 2 6. Anyone has any questions? Okay, so no, since nobody is having, we'll move to the third question. Semiconductor nanomaterials have dash properties. They exhibit wide band gaps. So I'm modifying them to show different properties: metallic, uh, metallic and non-metallic, non-metallic, metallic, non-metallic, and gaseous. So basically, I hope you guys are aware of what nanomaterial is. Sorry, what a band gap is. So basically, a band gap is the energy a electron needs to move from the valence band to the conduction band. So basically, if you see in the metals, the valence band and the conduction band. So the upper side is the conduction band, the lower side is the valence band. So the energy that you need to move the electrons from valence band to the conduction band is where is very less. So that there is no energy gap. There is no energy gap required. So that is why the metals are conductive in nature. So if you go to semiconductors, the amount of energy required is quite less. So the bandwidth is less. So then if you go into what do you say, no, insulators per se, the band gap goes on increasing. So because we have in a semiconductor, you can like they can act both as metals as well as non-metals because of the band gap. Because of the tunability of the band gap, it is called the it can show both metallic as well as non-metallic properties. Any questions? Okay, so we'll move to the next question. Read one of the following statements: zero dimension nanomaterial. In this, the one dimension will be in the nanoscale, and sorry, one dimension nanomaterial. In this, any one dimension will be in the nanoscale, and the remaining two dimensions are out of the nanoscale range. Nanotubes or nanowires are related to this class.
Sir,
Two
no video
dimension.
is seeing, sir.
Huh?
I'm
You are not
not
seeing.
able to see the video, sir.
Okay, okay. I'll just reshare again. Is it from long time or just for this question, sir? Is it coming now?
Yes, sir. Now okay.
So okay, so we'll resume with the fourth question. So read the following statement. So these kind of questions you can ask.
Sir,
You can
can I
expect.
can I see the sir second and third also?
Yeah, sure. We'll move to this. If you had a problem, you should have told me from earlier. I will definitely try to rectify it from there, because we don't. When we move to the presentation, we are not able to see your reaction. So please, you can feel free to interrupt me whenever you are possible. So the second question is ZNO, CDSC, and CDT are related to dash group of semiconductor materials. 2, 6, 2, 6, and 7. So basically, for semiconductors, this is the how the naming convention works. So 2 6 semiconductors are binary semiconductors. So there is like CDAC type of semiconductors. Then you can also have 1 6 or 3 6 kind of semiconductors, which are ternary semiconductor. That will be CuInSe two, like kind of. So there will be three structures. So that will be the ternary semiconductor. And there will be this other group, so that will be 1 6, 2 6, and 4 6 type of semiconductors. They're quaternary semiconductor. That will be like it will have like four elements, so that will be like Cu2, Zn, Sn, Se4. So these kind of semiconductors. So in this we have just two. It is a binary semiconductor, so it is 2 6 semiconductor, 2 6 group of semiconductor materials. I hope it is clear.
Sir, please describe one second, sir.
This one. Okay, so basically for semiconductors, the like first there are like see, first it will be like the normal semiconductor, that is like single element semiconductor, in which what you do is silicon is doped with uh, like either n type or p type. So that is the basic type of semiconductor. So that is like we have a silicon wafer. On in that we dope it with n group elements or its p group elements. So then it becomes an n type semiconductor or p type semiconductor. So when we go beyond it, so basically when we go beyond silicon, so we have different type of semiconductors. So like they first they are the naming convention is like this. So if we have a 2 6 group semiconductor, so you have um, like a that is called as the binary semiconductor. Then you have uh, one six or three six. So basically, you will have one out of either one or three, and the second group will always be group six. So you can always see everywhere the group six is always there. So you will have either two six if you have two six. So these are based on the metal series. So if you have the metal series, based on that, basically when you have a semiconductor made, this is what the naming convention works. So I hope you are aware of the in the periodic table you have the three type of three divisions of the periodic table. So you have group 1 2, then you have uh, the other groups on the so that contains sodium, magnesium, those kind of uh, lithium, sodium, those kind of groups. And then you have the right hand side where you have the oxygen, nitrogen, silicon. So then in the middle you have the metal group. So based on the metals, if there is any semiconductor, when you are making semiconductors from the metal, so that is how the naming convention works. So here you have a 2 6 semiconductor, that will be a binary semiconductor. Then you have a ternary semiconductor, wherein you have a group 1 and group 3, group 1 or group 3 mixed with 6. So you can have 1 6 or 3 6 semiconductor. In this, these are called as the ternary semiconductors. Then you have one uh, one 1626 or 46. So in that case they are quaternary semiconductors. So that is how the convention works. So basically, when if you are given a question, so you are most likely to be given either of the three questions. You will either have like what is CDSE, which type of group it is. You will have like, if you have three elements in that in the question. So here you have only ZNO, ZNS, CDS. Like it is a only two element type of semiconductor. So these are called as the uh, binary semiconductor or else group 26 semiconductors. If you have like more than that uh, semiconductors, so if you have three elements, so then it becomes a ternary semiconductor, and if you have four elements, then it becomes a quaternary semiconductor. So this is how the naming convention works for semiconductors. I hope I'm clear. So we move to the so the answer is 26. So we move to the third question. Semiconductor nanomaterials have the properties they exhibit wide band gaps for by modifying them to show different properties. Metallic, option A is metallic, option B is metallic and non-metallic, option C is non-metallic, option D is metallic, non-metallic and gaseous. So basically we'll just understand what is the concept of band gap. So band gap, basically every element has the valence band and the conduction band. Conduction band is basically where the electron becomes like you can like electron can be freely be flowing from uh, over the lattice. So whenever this any metal, so basically in the case of so to make the electron go from the valence band to the conduction band, you need some energy. So that energy is called as the band gap. Okay. So to move the electron from the valence band to the conduction band, you need some energy. That energy is called as the band gap. So now if you look at the this figure, you can see that there is the metals have the both conduction band and the valence band are just merged into each other. So you don't actually need energy to actually move the electrons from valence band to conduction band, and that is why metals are very good conductors. Okay. Then we come to semiconductors. So basically semiconductors, as you may know, have a like have some amount of band gap, and you might have even had those experiments where you have a Zener diode or those kind of diodes where you how you find the breakdown voltage. So breakdown voltage is basically the energy which you supply to the semiconductor, after which it becomes it becomes conductive, and it turns into a like a conductor, full-fledged conductor. And then there are insulators which have a very high band gap. So basically the energy that you require to move the conduction band, so the valence band electron to conduction band is very high. So there is no flow of electron that takes place. So now what the question is asking is, what properties do semiconductor nanomaterial have that so have by like through which you can they have a very wide band gap, and that can be modified to have different properties. So the you can tailor the band gap of the semiconductors to get either make them what kind of property. So can you tailor the band gap of semiconductor to make them metallic? Can you tailor the band gap to make it metallic and non-metallic? So you can make it either conductive as well as non-conductive. Can you only make them non-conductive? Can you make them conductive, non-conductive as well as gaseous? So this is a ridiculous option, but yeah. So these are the options. I hope you have understood the option. Please please select the answer what you feel. Okay, I'm not getting any option from your end, so we'll move to the answer. So, so the answer is metallic as well as non-metallic. Any questions? So we'll move to the question number 4. you have to read the following statement. So we have two statements given. So in the first statement states that one dimensional nanomaterial in this any one dimension will be in the nanoscale range, and the remaining two dimensions will be out of the nanoscale range. Nanorods, nano tubes, and nanowires are related to this class. Two dimensional nanomaterials, any two dimensions are in the nanoscale range, and the remaining two are out. These includes nanofilms, nanolayers, and nanocoatings. So the you have to choose the correct option. Whether statement one A and B are correct, only statement A is correct. Only statement B is correct, and only statement both statement A and B are false. So we already discussed what 0D, 1D, and 2D nanomaterials are. So this is again a refresher for you. Zero dimension nanomaterial, all the dimensions are in the nanoscale. uh, One dimension nanomaterial, one dimension, so either x, y, or z. One axis, along one axis the dimensions will be more than the nanoscale. Two dimension nanomaterials, either x, y, z, either of the two, x, y, y, z, or x, z, in one or two axes it will be more than the nanoscale range. And then the three dimension nanomaterial, in all the three axes it will be more than the nanoscale range. So based on the explanation, what do you think will be the right answer? Okay, so the answer is A. A and B are both correct. So basically, as I said again, one dimensional nanomaterial, at least one will be a- a- so any questions? So we move to the question number 5. Nano composites, core shells, multi nano layers, bundles of nanowires, and bundles of nanotubes are categorized as zero dimensional nanomaterials, one dimensional nanomaterials, two dimensional nanomaterials, or three dimensional or bulk nanomaterials. So as I said earlier, three like uh, uh, again you have in case of three dimensional nanomaterial, all the dimensions are more than the nanoscale, but they are like interconnected structures. So then you have like a structure that is combined, that is made by combining multiple nanowires. So the minimum feature size is in the nanoscale, but the final what you get the object is above the nanoscale. So that is called as the three-dimensional nanostructure. So the answer here is D, three-dimensional or bulk nanomaterials. No. So you have, when you have a composite, so we got answer as 1D. So no, actually when you have a composite, so you have the core shells or in composites or multi nano layer bundles. So basically you are bundling it. So you are making a like you are merging many things and you are making that structure. So then that structure becomes a 3D nanomaterial and not a 1D nanomaterial. So moving to the next question, fullerenes are dash particles of 60 or more carbon atoms, solid cage structure, hollow cage structure, particle filled cage structure, or solid hexagon. So basically, fullerenes are something like this football kind of structure. So basically, every you can see you can see every black dot here in this structure is a carbon atom. So basically, what happens is it looks like a football to a like if you actually go and see the structure. So basically, these are like more than 60 carbon atoms are like in a like each sheet is a hexagon, and then they come together to make a cage kind of structure. So what do you think will be the answer? Looking at the structure, what do you think will be the answer? Will it be, is it a solid gauge structure? It is a hollow gauge structure? Is it a particle filled gauge structure, or is it a solid hexagon? Yes.
Allocate structure.
Yes, correct. The answer is B. It's a hollow gauge structure. I hope this was easy question. We'll move to the next question. Using dash reduces the metal ions to metal nanoparticles. Oxidizing agents, salting agents, reducing agents, or acid reducers. So basically, sorry. Uh, Uh, Sorry, I forgot to get the schematic for it. So yeah, basically what happens is when you are making metal nanoparticles, so you will take some metal salt. So what you will do is if you are making like a you can say gold nanoparticle. So what you will do is you will get auric chloride. So you will dissolve it in water. Then you will stir it. Basically, you will stir it and you will make a solution, and then you will use some reducing agent. So basically, you will use something like ammonia or NaOH or something like that. That will make the like that will form that will lead to precipitation. So basically, what you use like to induce precipitation is called as the reducing agent, and so that you can get the metal ions. So basically, using metal reducing agent reduces the metal ions to metal nanoparticles. So we move to the next question. Read the following statement. A graphene precursor is graphene oxide whose electronic conductivity is very low. Um Converting graphene oxide to reduced graphene oxide gives better results with good conductivity. The statement A and B are correct. Only statement A is correct. Only statement B is correct. Both statement A and B are false. So the answer is statement A and B are both correct. So basically, graphene oxide has basically lot of oxygen kind of functional group. So basically, due to the presence of oxygen functional groups, the electronic conductivity is very low. So basically, you remove the oxygen. You, you basically then you remove the oxygen functional group from graphene oxide, and then you get the reduced graphene oxide, so that increases the conductivity of the structures. That is why you use reduced graphene oxide to make graphene oxide. Question number 9. Graphene is composed of carbon moiety. So basically graphene is composed of carbon moiety. Basically graphene is only made up of carbon. That is what the says. So don't think it is very fine. You will see it's a fancy word. So it's basically what it means, like graphene is only composed of carbon. That is what the statement means. Then statement B. The single layer carbon atoms are arranged in a pentagonal matrix. Graphene exists with infinite band gap, making it the best insulator, and the electronics are almost the massless particles. Uh, and electrons are almost the massless particles, which consist of the good electrical medium in 4 dimensions. Choose the correct option. Only A is correct. Only B is correct. Both A and B are false, and while C is correct, and statement A, B, and C all are correct. So, any guesses? Okay, so we'll move to the uh, explanation. So basically, the first question, first thing says that this graphene is made up of carbon moiety. So basically, it says that graphene is made up of only carbon material, carbon atom. So that is true. But you can see here how it is arranged. So it is arranged in a hexagonal matrix, not in a pentagonal matrix. So basically, it has 6 edges, not 5 edges. So basically, that is the related to your second statement, and then it comes to the third statement. So basically you can see the band gap. So basically it doesn't have a very wide band gap, so depending on the structure. So graphene has a very unique property. So based on how its geometry is, you will get a different band gap also. So if you can see from here, the based on the arrangement, the band gap changes. So basically, um, that is how the three statements come. So the answer is only A is correct. So graphene, depending on the graphene as a is only composed of carbon atoms. So that is the question one is correct. Question B, in a single carbon atoms are arranged in a pentagonal are arranged in a hexagonal matrix. So answer B is statement B is wrong. And then the statement three, basically graphene exists with infinite band gap, making it the best insulator. So no, graphene, depending on the configuration, it can be tailored to make an insulator as well as it can be used to make an conductor as well. So basically it depends on how you are changing the geometry or changing the like configuration of graphene. You can get different kind of properties. So the answer here is only one. Graphene is composed of carbon moieties. So now moving to the last question. To convert graphene oxide into reduced graphene oxide, dash methods could be used. So exfoliation method and CVD. Exfoliation method, CVD, thermal reduction and chemical reduction. CVD method, thermal reduction and chemical reduction. So I'll just give you an overview of what kind of what each process means before we go to the answer. So basically, exfoliation method is basically, you might have seen the exfoliate. Even in cosmetic, many of the cosmetics they say exfoliate. So basically, what do you do is basically use something like something to like machine it out. So basically you are just using something to just remove the what is there on the top. You can say per se like something like a haircut. So basically what you do is you use your scissor to just take whatever is not in the mm, not in line. So whatever all the undulations are there, they come out. So basically, you might have seen the carpenters basically just removing layer by layer. So that is one, that method is called as the exfoliation method. Then there is a chemical vapor deposition method. So here this is the schematic for it. So basically you have the chemicals here and the gas. So the chemical and gas and you have the chamber. So you have an argon chamber or nitrogen chamber. In this you like you put the chemicals in the at high pressure. So basically you put the chemicals at high pressure in the using in that chamber. Then in the gaseous phase, basically all the chemicals are put in the gaseous phase at high pressure in the chamber, and then the deposition occurs. So basically the deposition occurs. So last class we heard about PVD. So in the PVD we had a physical target basically that from which you would have the deposition occurring. Here you have the chemical form already. So based on the chemical form, it is supplied at very high pressure to the substrate, and then the deposition is occurring. So okay, we'll come to it later. So then um, we have the thermal method. So basically you have a precursor here, and you have this tower, this kind of structure. So you have a precursor, and then you allow you heat it under at a certain temperature, and then you will get your in an inert atmosphere. So you have a precursor and you have an inert atmosphere, and you heat it, and then you what remains is the nanomaterial. And then the last method is chemical reduction method, or the wet reduction method. In this basically the chemical is reduced. As I said, you will use the chemical metal salts, and then you will use the reduction agent, and then basically you will reduce the uh, you will reduce it to get the nanoparticle. So these are all the four methods. So one question I would like to ask you basically is, what do you think will have a higher deposition rate, a PVD or CVD? So please put that in the chat. And for the answer, basically to convert from reduced graphene to from graphene oxide to reduced graphene oxide, all the methods can be used: exfoliation method, CVD method, thermal reduction method, and chemical reduction method. So a hint basically to all of you, if these kind of question comes, the answer most probably will be all of them, because the researchers are continuously searching for new methods to actually make the nanomaterials, and that is a very easy way to get a paper also in nanomaterials field. So this is something which is very like, it goes on. So I would say that this will be like, many of the times your answer will be all of the above, unless it's a very specific thing which sir has mentioned in the class. Most of the time the answer will be all of the above. So that is one hint which I'm giving you, as so as to prepare you for the exam. So so for my questions, what do you think will have the higher deposition rate, PVD or CVD? Physical vapor deposition have a higher deposition rate, or a chemical vapor deposition?
CBD.
It will be chemical vapor deposition actually. So what is happening is, here, just to give you an overview, why is it so? So basically, in physical vapor deposition, you are having a atomic level deposition. So basically, as we read, as we saw in the last time, you are having a target. You will have a gold target. You will have argon gas atoms hitting the gold target, and then another gold atoms will be ejected, and then it will be deposited on the silicon wafer. But here, so what will happen? So so the deposition will be atomic rate, atom wise deposition, and you'll have a very good control over the geometry. So basically, if you want to make even like up to angstrom level, you can get the precision of deposition. If you can get at the angstrom level. So that is not possible with CVD. CVD has a very faster deposition rate. CVD already has the chemicals in the gaseous form. So basically, it is just going and depositing the chemicals. So there is no atom ejection or something going on. So directly the chemical layer is forming on the surface. So obviously it will be it will be faster, but you won't get a very good control over the thickness. So the control will be less. So that is how the thing works. So this might be a question that might be asked to you. So yes, we have finished this assignment. I know this was a short assignment, and you can expect all the assignment to be short assignments only. They are not very deep, but we'll try to give you some, like, more or less some more ideas, or some more in depth, whatever I know, or whatever tricks and tips and tricks I can give you. So if you have any questions, you can unmute yourself and ask. You can put in the group chat. If you don't have any questions, you are free to leave the meeting. I wouldn't keep you waiting here. Thank you. These questions are from the second week's lecture. So I also saw the lectures. So many lectures are not having all the content. So you need to go through the syllabus also. So these are from the second week two lectures. So this is the second live interaction session. These are from the week two lectures. Next week we will be doing week three lectures. Any other question? Yeah, yeah, you have asked a very important question. So yeah, the questions here, these are the previous year questions. So if you had given this exam in the previous semester, in the previous time it was being offered, you would have gotten these questions. So now basically what we are supposed to do is, we are supposed to solve these previous year questions, so that you have an idea how to solve this year's questions. So whatever questions will be asked this year, I hope that whatever questions we do will help you in solving this year's questions. And also, what is majorly important is, basically what happens is, many of the previous year assignment questions, or the previous year questions get come through in the final exam. So in order to help you in that sense, we are doing this. So one is to help you with the this year's questions. If you have any questions with this year which you are not able to solve, you are free to ask in this kind of in this sessions. If you have any doubts, if you know what the question is, and if you have any doubts, you can surely ask. Uh, but you have to type the full question here with the options, because I cannot go to that screen during the lecture. So you'll have to maybe copy paste the entire question if you have any question. And the other thing, these are supposed to basically help you, give you some tips and tricks of how to solve the question paper. So that's how it is. I hope I answered your question. Kavya madam, you had asked where you want previous year's question papers. So I'll just show you how to access it. I'll just stop sharing my screen, and just a moment. So I'll show it to you how to access it. Um, I I hope my entire screen is visible now. So you can see here we went to the Swayam portal. So this is the Swayam portal. So from here we went to my courses. So here we went to my courses. So these are the courses. You will get the courses list. So here you go to your course. So can you see this? You are gone to into the course page. So once you go to the course page, here you have the problem solving sessions tab. So if you go here, problem solving sessions, recordings. So if you go here, you will see click here. So once you click here, you will have this folder open. So this is the folder in which you have the PPTs. So this is the only way you can access the previous year. So these PPTs have the previous year questions of the assignments, and here you can access the PPT. This is how you can access the PPT. So I hope you know now how to where to get the sessions. So you have to go
Yes,
here,
sir. Thank you.
recordings. Yeah. Uh, so I'll stop sharing my entire screen. Okay. So yeah. So the Debrata sir has asked a very important question. So how do we control pests using nanotechnology? So basically, there are three technologies that have been used. In one of the cases, what they are doing is they are using repellent. So basically, they are developing nano repellent. So what will happen is when the pest is coming in the vicinity, that is so if it so puts if it comes in the vicinity, and if it touches it, it will basically release this foul smell. So basically, why nanotechnology is being used? So you have to understand why nanotechnology and what is being used, because nanotechnology allows for control. So the control which is not possible by the by normal methods, nanotechnology allows for control. So you can make something like pH responsive or thermal responsive. That can be only done using nanotechnology, because nanotechnology allows you that thing. So you might have seen one of the Mortine or something which had the mouse pad. So basically, in which the mouse would just when the mouse would walk over it, it would just get attached, and it would not be able to move. So those kind of inventions are being made using nanotechnology. So basically, what will happen is the pest will just go and stick there. The second one is when the pest is going nearby, it will like based on if it goes in like it will be like a balloon basically. So when the pest is just going near the plant, and when we the it has been kept, It will just go because of the pest. It will get exploded, the balloon kind of thing, and that will give out the and pest repellent. So there are like two three technologies that are being developed, and these are in uh, these have been used like maybe in research scale. I won't say they are being used in like actual settings, but these are two three technologies that I read about. Maybe I'll try to link those, find the link for those also, and share it with you in the next class. Any other question? I'm also attaching here article, a link for an article which I had read few weeks back. So you can check this also. Maybe it will be of use. So you can just Debrata sir, you can just check using the just copy paste the article from the chat box. Anyone has any other questions? If you don't have any questions, we'll maybe just go to the other question. So for the people who are joining now, we'll just go through all the questions again. So these are the questions which were asked last year as part of assignment 2. So the first question is, in dash, all three dimensions of the nanomaterial are in the nanoscale. Nanoparticles, these nanoparticles will come in the into this classification. Basically, that is the question. So it is whether it is zero dimension nanomaterials, one dimension nanomaterial, two dimension nanomaterial, or three dimension nanomaterial. So the answer is, so basically what happens is, nanomaterials can be classified into four types: zero dimension, one dimension, two dimension, and three dimension. So basically, zero dimension nanomaterial, all the dimensions are in the nanoscale. In the one dimension, one of the axis, so either x, y, or z, one of the axis is not in the is not in the nanoscale. Others are in the nanoscale. In this in this in 2D nanomaterials, basically, um, uh, two dimensions are not in the nanoscale, one is in the nanoscale. And in the three dimensional nanomaterial, all the three dimensions are not in the nanoscale. So basically it is mainly more of composites and those kind of structures which are made by so like if you make a uh, structure that is composed of multiple nanowires or multiple nanosheets, that is called as the three dimensional nanomaterials. So in this, answer is zero dimensional nanomaterials. So then we move to the second question, that is, ZNS, ZNO, CDS, CDAC, and CDT are related to dash group of semiconductor materials, 2, 6, 2, 6, and 7. So this is how the naming convention happens. So basically, you have group 2, 6 semiconductors, which are binary semiconductors. You have group 1, 6 or 3, 6 semiconductors, which are ternary semiconductors. Then you have like group 1, 2, 6 and group 1, 4, 6 kind of semiconductor, which are called as the quaternary semiconductor. So in this, the answer is 1, 6 semiconductor. Then question number 3, semiconductor nanomaterials have dash properties. They exhibit wide band gap by modifying them to show different properties: metallic and non-metallic, non-metallic, and gaseous. So basically, um, what is band gap is basically the energy. So there are the electron is basically all the is in the valence band. So basically, when you want to move a electron from the valence band to conduction band, so conduction band is basically when the electron basically starts moving. So the motion of electrons is possible. So we need to find out. So what happens is energy is required to basically move the electron from the valence band to conduction band. So that energy is called as the band gap. So in case of metal, you can see the valence band and the conduction band are basically the same. So there is no specific band, there is no specific energy required to for the electron to move from the valence band electron to move. So that is why metals are very good conductors. Then you have semiconductors. So you might have even had this experience in your school and college also, when you had a Zener diode and you would supply the potential, and then after a certain potential, there will be a breakdown, and you will have the semiconductor acting as a conductor. So the basically that energy, that voltage you are supplying is basically called as the band gap energy or band gap voltage, and that forms the like how the bulk semiconductors work. And in case of insulators, basically the band is so big, it is impossible for the band electron to move to the conduction band. So because of that, the insulators are always insulating in nature. They do not actually turn into conductor. So basically, in case of semiconductor nanomaterials, the band gap can be tailored. So band gap can be modified such that you can even get make it a metallic, as well as you can get a non-metallic or an insulated type of band gap. So that is the property of the semiconductor nanomaterials. Moving to the fourth question, you have to read the statement. So basically, in this, um, um, you have to read the statement. So that is like zero dimension, one dimensional nanomaterial. In this, any one dimension will be in the nanoscale, and the remaining two will be out of the nanoscale. Nanorod, nano tubes, or nanowires are related to this class. Two-dimensional nanomaterials are basically are two of the dimension is in the nanoscale, and the remaining one is out of the nanoscale. Uh, these include nanofilms, nanolayers, or nano coating. So basically, the answer is both A and B are false. So in one dimension nanomaterials, both uh, only one dimension will be in the one one dimension will be out of the nanoscale, other two will be inside the nanoscale. In the two-dimensional nanomaterial, two dimensions will be out of the nanoscale, and only one dimension will be in the nanoscale. So that is why that is the answer. So the answer is D. A and B are both false. So in this, I made a error. So I will correct it while before uploading the um, PPT. Question number 5, nanocomposites, core shells, multi nanolayers, bundles of nanowires, and bundles of nanotubes are categorized as zero-dimension nanomaterials, one-dimension nanomaterial, two-dimension nanomaterial, three-dimension nanomaterial. So the answer, as I said earlier, three-dimensional nanomaterials are basically composites of various type of 0D, 1D, or 2D nanomaterials. So you are making them by combining the other type of nanomaterial. So that is what it is. So the core nanocomposite core shells, multi nanolayers, are basically three-dimensional nanomaterials. Question number 6. Fullerenes are dash particles with 60 or more carbon atoms, solid cage structure, hollow cage structure, particle filled cage structure, or solid hexagon. So basically, fullerenes are basically like a football kind of structure. They look like a football. So you can call them as the hollow cage structure. Then moving to the next question. Dash is using dash reduces the metal ions to metal nanoparticles, oxidizing agent, salting agent, reducing agent, acid reducers. So the answer is reducing agent. So basically, what happens is you have um, metal salt. So if you are making any nanoparticle, making gold nanoparticles, so what you will do is you will take gold salts and then dissolve in water or any medium. You can many of the things, many of the salt you dissolve in ethanol or some other solvent also. So what you will do is you will dissolve in so you will make a solution, and then you after that you will use a reducing agent. You will use something like ammonia or some other reducing agent, and you will convert that metal ions into metal nanoparticles by inducing precipitation by using the reducing agent. So the answer is use the reducing agent. So the following in the eighth statement 8, graphene precursor is graphene oxide whose electronic conductivity is very low. Uh, Converting graphene oxide to reducing graphene oxide gives better results with good conductivity. Um, Choose the correct option. Statement A and B are correct. Statement A is correct. Only statement B is correct. Both statement A and B are correct. So the answer here is basically both statement A and B are correct. So basically what happens is in graphene oxide, because of the oxygen functional group, the conductivity is low. So in reduced graphene oxide, you remove the oxygen functional group and you get good conductivity. The statement 9, graphene is composed of carbon. Question 9. In this again you have to read the statement. Statement A, graphene is composed of carbon moiety. In graphene, the single layer carbon atom are arranged in pentagonal matrix. Graphene exists with infinite band gaps, making it best insulator, and the electrons are almost massless particles which consist of good electrical medium in 4D. Only A is correct, only B is correct, both A and B are false, but C is correct. All statement A, B, and C are correct. So basically, what is graphene consists of carbon moiety is basically it only consists of carbon atoms. So basically, uh, what that statement means is that graphene is only composed of carbon atoms, and which is true. So basically, it is carbon atoms are arranged across a hexagonal matrix. Here you can see the structure. At every edge there is a carbon atom, and they are arranged in a hexagonal manner. So one of the main thing about graphene is basically how you the geometry or how you have configured graphene. You get different kind of band gaps. So basically, you can see here the band gap changes depending on the configuration of graphene. So basically, the answer here is the only correct statement is statement A, that graphene is composed of carbon moieties. The other statements are wrong. Basically, it is a hexagonal matrix and it doesn't have an infinite band gap, making it doesn't have an infinite band gap. It can be used both as an insulator as well as the conductor based on how you configure it. Moving to the 10th question again, to convert graphene oxide to reduce graphene oxide, the following methods are used: exfoliation method and CVD method. Exfoliation method, CVD method, thermal reduction, chemical reduction. CVD method, thermal reduction, and chemical reduction. So the answer is exfoliation method, CVD method, thermal reduction, and chemical reduction. So it is basically all the different methods can be used. So just to give you an overview of how each method looks, so basically you have an exfoliation method in which basically you exfoliate. So basically you might have heard many of the cosmetic products exfoliate your skin, exfoliate and this that. So basically what it does is basically it removes the undulations on the surface. So at the surface level, so it just rubs on the surface and nanoparticles are generated. Uh, in the chemical vapor deposition method, basically you have what we discussed last time. You have a gas chamber, in which you put the substrate and you pass on the chemicals at very high pressure, and it reaches the substrate and it is deposited on the substrate. The chemical is deposited on the substrate. Then in the thermal reduction method, basically you put the precursor, you put up inert gases, and then you heat the structure so that you get the nanoparticle. And in the chemical reduction method, basically you use metal salts, and then you use a reducing agent, and then you make the nanoparticles. So that is how the process works. So this is the answer: exfoliation method, CVD method, thermal reduction method, and chemical reduction method. So, is there any questions? If you don't have any questions, you can leave the session, or else you can just put your questions in the chat box as well. In case you don't have any question, you are free to leave the session. So, anyone has any questions? Anyone have any questions? Any questions? Anyone has any questions? Anyone has any questions? Any questions? Uh, since there are no more participants, I would like to thank you all for your time, and we'll see you next week. Thank you for your time and patience.